We'll now show how we use these Boolean operations in what we call logic gates. A gate is simply an electronic device that operates on a collection of binary inputs to produce some binary outputs. The idea is that it transforms a set of 0, 1 input values into a single 0, 1 output value, and this is according to a specific transformation rule. Now, the gates can implement a wide range of different transformation rules. The ones that we're concerned with are those that involve the Boolean operations and, or, and not. So we're going to take a look at 3 different types of gates, which what we call the AND gate, the OR gate, and the NOT gate. Here is the symbol for the AND gate. So here A and B are Boolean values. And unlike what we were doing before with the Boolean operations, A and B in here are going to be zeros and ones, not true or false, although they pretty much represent the same thing. So the idea with these gates is that we have these values of A and B going into this symbol here, which we denote as the AND gate, and then the output, which goes in this direction, would be the result of A and B. So here's the truth table for that. And once again, I said that we're dealing with zeros and ones now instead of trues and falses. But it's pretty much the same thing. So if A and B are both 1, then A and B is going to be 1. If either A or B or both are 0, then A and B is going to be 0. But this is just to show what an AND gate looks like. And we're going to see some examples later on of how we would combine these with the other gates to create different types of circuits. Here's the symbol for the OR gate. So notice it looks a little bit different. The picture itself, the drawing is a little bit different. There's a plus in the middle part, the gate part itself, instead of a dot, because that's the notation that we use for an OR. And so once again, we have values of A and B going into this gate, and then the output is going to be the result of A or B. And we have the truth table for it, where we can see once again it's a bunch of ones and zeros. So as long as A or B or both has a 1 in it, then A or B is going to result in a 1. But if both A and B are 0, then the output of this OR gate is also going to be 0. And then here is the symbol for the NOT gate. So yeah, it's just a triangle with a little circle in front of it. But the idea is the value of A, whether it's 1 or 0, goes into the NOT gate. And then what comes out of it is going to be the other value. So here's our truth table for it. So if A was 1, then NOT A is going to be 0. And if A was 0, then NOT A is going to be 1. We'll now show how we can use these 3 different types of gates to construct computer circuits. A circuit is a collection of logic gates that transforms a set of binary inputs into a set of binary outputs, and in which the values of the outputs depend only on the current values of the inputs. So let me give you an example of this circuit. So here we have a circuit which we call C, and we have M binary inputs and N binary outputs. So what we have here is, let me show you the picture here. So we have on the left side M inputs, so they're going to go into this circuit, and the circuit's going to do some type of computation, and then the output will be N outputs. Yeah, so I mean, these gates inside the circuit C can be interconnected in any way. So we're going to use a combination of AND gates, OR gates, and NOT gates. And there may be some other types of gates, but we're not really going to worry about them in this class. The only ones we're going to worry about are AND, OR, and NOT. But inside this circuit, there could be any combination of these gates. They can be connected in any way, as long as the connections do not violate the constraints on the proper number of inputs and outputs. So the number of inputs should be whatever M is, and the number of outputs should be whatever N is. So like, for example, each AND and OR gate must have exactly 2 inputs and exactly 1 output. Each NOT gate must have exactly 1 input and 1 output. But the whole point here is that we have a bunch of these inputs going into this circuit. It does some type of computation, and then we get a bunch of outputs based on the result of the computation. Here is another example of a circuit that uses all these gates. So here we have a diagram of a circuit that has 2 inputs, which we label as A and B, and 2 outputs, which we label as C and D. And we see that we have one AND gate. So we have the AND gate right here. So I'm just going to put AND right here so we know this is our AND gate. We have one OR gate, which is up here. So there's our OR. That's not a good R. Let me try again. OR, come on. Close enough. And then we have two NOT gates. So we have a NOT gate here. And then we have another NOT gate over here. We'll go with it. And what we find here is that there is a direct relationship between Boolean expressions and circuit diagrams. So in fact, every Boolean expression can be represented pictorially as a circuit diagram. And every output value in a circuit diagram can be written as a Boolean expression. So for example, let's say we want to try to compute the values of C and D. Now, what's going to be C? Well, it's going to be A or B because we have this OR gate up here. So the value of A is going to go in here. Lovely arrow, but we'll go with it. The value of B goes in here. And then its output is going to go all the way to C. So C in this case is going to be whatever A or B is. And then what about D? Well, D is going to be a little bit more complicated. It's going to be the NOT of the quantity of A or B and not B. Well, how do we get that? Well, the not B is taken care of down here. So this NOT gate gives us not B. And then the AND gate is going to give us the AND of not B. And then the OR of A or B. So we follow this circuit down to this part of the input for the AND gate. So this gives us the A or B and not B. So that gives us this result. And then we put that into a NOT gate. So then that output is going to be whatever D is. So that's how we get not A or B and not B. The value that appears on any output line of a circuit can be determined if we know the current input values and the transformations produced by each logic gate. So let's just use this circuit again as an example to see if we can compute some stuff. So let's just say A is 1 and B is 0. My claim here is that C is going to be 1 and D is going to be 0. So let's kind of walk through this circuit and see how we would actually get that. So we first have our input values of A and B. So A would be 1, B will be 0. So let's compute A or B. Well, 1 or 0 is going to be 1. So the output of A or B is going to be 1. So then that means the result of C is going to be 1. So sure enough, C is definitely 1. It's the result of A or B. Now let's figure out D. Well, we first need to take care of the not B part. So not 0 is going to be 1. And we also know that the other input for our AND gate is going to be the result of A or B. So that's going to be 1. So 1 and 1 is going to be 1. So the not of 1 is going to be 0. So sure enough, this is how we can use the circuit to evaluate our expression or evaluate the circuit itself.